It began as a faint flicker in the darkness, a dot so unremarkable that most telescopes ignored it. Yet, within days, that quiet speck tore through the astronomical silence with something no one could explain. The object named 3I Atlas wasn't just another traveler from beyond the solar system. It was rewriting the rules of how such visitors should behave. When the Atlas survey in Chile first picked it up in July 2025, it seemed predictable, an interstellar body on a hyperbolic trajectory, rushing toward the sun at nearly 130,000 miles per hour. But then, the light began to pulse in a way that defied expectation. Its brightness didn't fluctuate as comets usually do. Instead, it dimmed and brightened erratically, like something turning slightly on an invisible axis, but far too slow, far too uneven. What caught astronomers off guard wasn't its speed, or even its strange CO2-rich coma detected while still 5 astronomical units from the sun. It was the timing. Outgassing had begun before sunlight could have possibly heated its surface enough to cause sublimation. Something was triggering activity out there, beyond the frost line, in a region where most comets remain inert. Within weeks, observatories across the world confirmed the data. The James Webb Space Telescope detected an unusually low water signature, combined with negative polarization patterns, a scattering behavior no one could model. The comet's faint anti-tail, pointing toward the sun instead of away, added one more impossible layer. And as 3I Atlas approached its October 30th, 2025 perihelion, the question deepened. Was this object breaking the laws of thermal physics, or revealing that we never truly understood them? When we first modeled the trajectory of 3I Atlas, everything appeared straightforward. A clean hyperbolic orbit, a predictable inbound velocity, and a solar approach that matched the dynamics of any interstellar object entering from deep space. But the data quickly began to misbehave. As the object closed to within 4 astronomical units of the sun, its coma expanded asymmetrically, and the nucleus seemed to lose coherence, not through fragmentation, but through a kind of flickering instability, as if light itself was being scattered by a surface we didn't yet understand. Spectroscopic readings from both JWST and the Very Large Telescope revealed something that forced us to re-examine our assumptions: a CO2-dominant emission spectrum with vanishingly little water vapor. That ratio, roughly 10 times more carbon dioxide than water, simply didn't align with any known solar system cometary chemistry. The coma's polarization was strongly negative, an optical signature suggesting the dust particles were smoother and possibly coated with exotic organics or amorphous carbon, unlike the porous, icy grains typical of comet tails. Even more puzzling was its thermal inertia. The temperature of 3I Atlas's sunlit side didn't rise as expected. Instead, it plateaued, holding steady at a value far below the theoretical threshold for the observed outgassing. The implication was unnerving. Something other than solar heating was driving its activity. Could the object's rotation have exposed volatile-rich fractures in a rhythmic sequence, or was it responding to internal pressures from trapped gases frozen since interstellar space? Astronomers began to compare notes, and contradictions multiplied. The Gemini North Telescope detected localized jets emerging perpendicular to the object's spin axis, but the rotation period, measured by brightness curves, didn't match those jets' timing. The surface appeared to flare without rotation correlation, like an engine firing out of sequence. For a few nights, the comet appeared almost calm. Then, on August 19th, instruments from the European Southern Observatory reported a sudden brightening by a factor of 3, without any change in solar proximity or viewing geometry. Light scattered off a newly formed anti-tail that curved gently sunward, composed not of gas, but of micron-sized dust grains pushed inward by gravitational alignment rather than repulsion. Physically, it shouldn't happen. Yet there it was, caught in repeated exposures, undeniable. The orbital modeling team at JPL tried to reconcile it through known mechanisms: radiation pressure, jet torque, or fragmentation debris. But none of them fit. The forces needed to create that dust configuration would tear the nucleus apart, and yet 3I Atlas held together stubbornly intact. It was as though we were witnessing not a breakdown of a comet, but a misunderstanding of what interstellar bodies truly are. And as the data piled up, one impossible question began to circulate quietly through the observatories. If this isn't behaving like a comet, then what is it? The idea that 3I Atlas might not be a comet was at first treated as heresy. After all, labeling an interstellar body as anything else invites more questions than it answers. But the evidence didn't care about consensus. The thermal models failed. The gas ratios didn't match any cataloged body. The shape of its light curve defied rotational physics. Each new observation peeled away one layer of assumption and replaced it with quiet confusion. In early September 2025, as it crossed the orbit of Jupiter, a coordinated campaign began. JWST, Hubble, Gemini, TESS, and multiple ground-based networks observed it almost continuously. The goal was to determine whether 3I Atlas's emissions followed any cyclical or mechanical pattern. But instead of periodicity, they found chaos. Its CO2 jets ignited randomly, and the dust production fluctuated independently of heliocentric distance. The key anomaly was what we called the reflection deficit. Polarimetric measurements suggested the object was reflecting less sunlight than its size and albedo predicted. Either its surface was absorbing nearly everything, or the coma itself was diffusing light in an unexpected geometry. Some theorized that the grains were amorphous carbon silicates, the kind formed only in the outermost shells of carbon stars. Others pointed to the possibility that the grains were magnetic, aligning under solar-wind interactions and scattering light directionally. Even its spin was a mystery. Unlike Oumuamua, which tumbled chaotically, or Borisov, which spun predictably, 3I Atlas seemed to precess, a slow, uneven drift that shifted its jets and tail orientation over time. The comet's light polarization angle rotated opposite to its observed spin direction, implying a secondary motion, a kind of internal slosh or wobble caused by uneven mass distribution. Spectroscopy in mid-September revealed something stranger still. A spike in cyanide emission accompanied by a temporary suppression of CO2. That should be impossible if sublimation was driving both. For a week, no one could explain it. Then a group from the University of Arizona proposed an unsettling hypothesis, that we weren't seeing chemical depletion at all, but surface collapse, as if the crust was breaking apart and exposing deeper layers temporarily shielded for eons. If that's true, 3I Atlas isn't just anomalous. It's fragile, perhaps near the end of its structural life. But even as that theory gained traction, another data point shattered it. Radar reflections from the Goldstone Deep Space Network showed a consistent radar cross-section, no fragmentation, no scattering debris. The surface was holding firm. It was behaving as if physics itself had two sets of rules, one that applied to our solar system and one that governed the travelers who came from beyond. And that led us to a new kind of fear, that maybe the impossible wasn't an error in our instruments, but an error in our understanding of the universe itself. By late September, the tone of the scientific community had shifted. What began as curiosity had turned into cautious disbelief. Each dataset was meticulously checked, recalibrated, and reanalyzed, yet the anomalies persisted. Stubbornly immune to correction, the comet's behavior wasn't a byproduct of error. It was real. The Atacama Large Millimeter Array, ALMA, detected faint millimeter wave emissions that hinted at an unexpected property, a dense, compact inner core surrounded by a porous, low-density shell. That configuration would explain some of the uneven outgassing, but not the impossible consistency of its structural integrity. Normally, with that much volatile loss, a comet's surface fractures, collapses, or disintegrates into a cloud of fragments. But 3I Atlas was solid, eerily stable. Then came the most dramatic observation, a torque reversal in its rotation. Between September 24th and October 1st, light curve analyses revealed that the direction of its slow spin had reversed. Not slowed, not paused, reversed. No known physical mechanism could cause this without massive jet asymmetry or catastrophic breakup. Yet the object remained whole, drifting silently toward its October 30th perihelion. Some proposed that radiation pressure from its reflective anti-tail could, in theory, generate a net torque under highly specific conditions, but that explanation crumbled under calculation. The energy required was orders of magnitude higher than what solar radiation could deliver at its current distance. Others speculated on electrostatic forces, an induced charge interaction between the coma and solar wind, but even that fell short. It was around this time that JWST captured its most haunting image yet. A faint, bifurcated plume extending both toward and away from the sun, like two exhalations in opposite directions. The symmetry was unnatural, the kind of balance nature rarely achieves by accident. If one side was driven by gas release, the other should have dissipated, but both sustained equilibrium for nearly 36 hours before fading into the void. Astrophysicists began to whisper what few dared to publish. Perhaps this wasn't an inert relic from another star system. Perhaps it was reacting, not to the sun, but to interstellar conditions embedded in its own structure. That idea, radical as it was, aligned with something subtle but profound: the interstellar memory hypothesis. The notion that matter formed around different stars retains its own chemical rhythms, a thermodynamic signature shaped by alien starlight. If 3I Atlas carried within it the thermal code of another sun, its reactions might simply appear impossible to us because they were perfectly natural to it. Still, one problem remained. The energy output during those emissions exceeded any plausible internal reservoir. If it wasn't self-heating, then something else was feeding it energy, and the source was nowhere to be found. It was at that moment that the astronomical community realized the object wasn't defying physics. It was revealing the parts of physics we'd never met before. The approach to perihelion was like watching a storm gather in slow motion. Every night, 3I Atlas revealed a new contradiction, and every day, we tried to explain it away. But by mid-October, explanations had run out. The comet's luminosity curve flattened when it should have peaked, its dust-to-gas ratio inverted, and its coma temperature, instead of rising as it neared the sun, fell by nearly 20 degrees Kelvin. That last measurement sent ripples through every observatory on Earth. It was the astronomical equivalent of watching ice refuse to melt under a blowtorch. The data were cross-verified by JWST, Hubble, and the Subaru telescope in Hawaii. All told the same story. As 3I Atlas approached the region where solar heating should have dominated, it was cooling. We double-checked calibration, even tested for light curve contamination by background stars. Nothing changed the numbers. Something was absorbing more energy than it emitted, an impossible heat deficit in open space. That paradox ignited a new line of reasoning. Maybe, instead of reflecting sunlight, its surface was transducing it, converting photon energy into chemical bonds or phase transitions within its carbonaceous material. A process like that had never been observed in a natural object, but certain forms of amorphous carbon are capable of trapping energy at the atomic level, releasing it later as delayed radiation. Could an interstellar grain aggregate amplify that effect on a macroscopic scale? Spectroscopy lent weight to the theory. The infrared emission lines shifted subtly with time, suggesting a continuous rearrangement of molecular bonds. It was as if the object was rebuilding itself as it moved closer to the sun, reorganizing its crust layer by layer. If true, that meant 3I Atlas wasn't merely surviving solar heating, it was adapting to it. During the week of October 15th, a set of high-resolution images from Gemini North showed transient streaks emanating from the nucleus, thin, radiant arcs that lasted minutes before dissipating. Each arc corresponded with spikes in CO2 emission, timed almost rhythmically, like breaths. To call it biological would be absurd, yet the pattern was unmistakably cyclic, reactive rather than random. This was no ordinary outgassing. It was a thermodynamic response, an equilibrium behavior under a completely alien rule set. The press began calling it the breathing comet. Scientists hated the nickname, but deep down, many of us felt the unease it carried. Because beneath all the chemistry and equations, there lingered a terrifying simplicity. This object behaved like it knew how to survive. The night before perihelion, 3I Atlas brightened one final time, a flare visible even through thin atmosphere in the Chilean desert. Its glow cut through the black like an ember refusing to die. And then, it dimmed. Not gradually, but suddenly, as if it had crossed some invisible threshold between comprehension and the impossible. When dawn broke over the Atacama Plateau on October 30th, every telescope that could point toward the sun's vicinity was already locked on. The day of perihelion had arrived, the closest approach of 3I Atlas to our star. Predictions varied wildly. Some expected it to disintegrate. Others believed it would flare violently. A few hoped for nothing but quiet data. None were prepared for what actually happened. At precisely 0743 UTC, the comet reached 1.4 astronomical units from the sun. Instead of fragmenting under thermal stress, it stabilized. The brightness froze, steady and unwavering, for nearly 6 hours. Its spectrum flattened into a smooth, featureless curve. No absorption lines, no emission spikes, just a continuous band of light as if its surface had turned mirror smooth. It was as though the object had shed its identity, disguising itself in perfect optical silence. Every spectrograph on Earth struggled to find definition in that light, but there was none. The photons that left its surface carried no information, pure radiation, without texture, a physical impossibility. The James Webb Space Telescope captured thermal data suggesting that the outer crust had reached a strange form of equilibrium. The surface temperature didn't rise above 200 Kelvin, far colder than any known comet under such solar exposure. In that frozen calm, jets ceased, the coma thinned, and the anti-tail, that eerie sunward plume, dissolved completely. For a brief window, it looked almost motionless. And then, at 1312 UTC, it released a faint pulse of infrared radiation that rippled outward like a sigh. Every instrument caught it, a sharp increase in mid-IR flux, lasting exactly 21 seconds. The flare wasn't energetic enough to imply explosion or sublimation. It was simply light released without cause. Some theorists speculated that the object had undergone a structural phase shift, a rearrangement of its molecular lattice, temporarily absorbing sunlight and releasing stored energy in quantized bursts. But that would make it not a comet at all, but a kind of cosmic capacitor, discharging energy absorbed over interstellar eons. When the flare faded, the brightness dropped by 2 magnitudes. To the naked eye, it appeared to vanish, swallowed by the radiance of the sun. Yet deep imaging revealed a faint trail continuing outward, unchanged in velocity but slightly altered in trajectory, as if the entire body had lightened, shedding some fraction of its mass invisibly. No debris, no dust, no fragments, just absence. And that's when the cliffhanger emerged, a pattern no one could ignore. The outbound path of 3I Atlas wasn't perfectly hyperbolic anymore. Its eccentricity had shifted, subtly, impossibly, toward a bound orbit. If confirmed, that would mean one thing. The interstellar object hadn't left us at all. It had decided to stay. In the aftermath of that impossible orbital adjustment, chaos rippled through the scientific community. Every orbital simulation was rerun. Every dataset was checked for computational drift. The Jet Propulsion Laboratory, ESA's Gaia team, and the Minor Planet Center all produced independent calculations, and each one came back with the same disquieting result. The eccentricity of 3I Atlas had indeed decreased below 1. Theoretically, it was no longer on an escape trajectory. That simple number broke astronomy's sense of order. An interstellar object cannot just change its mind and remain bound to the sun. Momentum is not optional, and energy doesn't disappear. Yet here was 3I Atlas, its velocity curve bending, its projected path looping faintly through the outer solar system as if caught in a net that didn't exist days earlier. No jets were firing, no visible mass loss, no torque signatures. The only plausible force capable of altering its orbit so dramatically would be a massive ejection of material, but none had been observed. The body seemed perfectly inert. Speculation became desperate. Some theorists invoked Yarkovsky acceleration, the subtle push from uneven thermal radiation. Others imagined electromagnetic coupling between the CO2 coma and the solar wind, creating a plasma drag effect. But the magnitudes were wrong, off by factors of thousands. It wasn't enough. Then came a more unsettling idea. What if 3I Atlas had not lost energy, but absorbed it? The perihelion event, that brief 21-second infrared flash, could have represented a quantum-scale restructuring of its molecular lattice, an exothermic reset. If its material composition allowed it to store solar radiation within deep carbon frameworks, it might have altered its own momentum subtly through internal redistribution. Essentially, it could have used light to rewrite its orbit. No mechanism in classical physics permits that, but the interstellar memory hypothesis resurfaced again. If the grains and carbon matrices of 3I Atlas were formed under the radiation spectrum of a different star, perhaps they responded to sunlight not as heat, but as information, realigning molecular bonds in a way that changed their interaction with gravity itself. The more we tried to explain it, the deeper the hole became. For the first time in decades, astrophysicists were openly admitting we might be facing a category of matter unrecognized in our models, something between solid and plasma, between chemical and quantum. Weeks later, as it receded beyond Mars's orbit, the object's brightness leveled again. The bound trajectory held steady. It was faint, but still there, our first permanent visitor from another star. And as silence settled over the observatories, one question refused to fade. If 3I Atlas chose to stay, what else might already be here, waiting to be seen? Now, months after that October perihelion, 3I Atlas drifts quietly through the darkness between Mars and Jupiter, dim, stable, and inexplicably bound. Its coma is gone, its outgassing ceased, and yet the faint reflection from its nucleus still carries the unmistakable signature of motion under unfamiliar rules. To the naked eye, it's nothing more than another cold fragment of rock. But to every astronomer who followed its passage, it's a question that still echoes through the heart of science itself. We once believed interstellar visitors were brief, messengers that arrive and vanish, leaving only mystery behind. But this one stayed. Its altered orbit, its impossible cooling, its defiance of solar physics, none of it fits within our equations. It has forced us to face a quiet but profound truth. Perhaps the cosmos is not uniform in its laws. Perhaps every star forges not just light, but a different version of physics. Looking at 3I Atlas now feels less like studying an object and more like observing a boundary, a threshold between what we know and what we still fear to imagine. It doesn't roar across the heavens. It just moves with an ancient patience, as if carrying the rhythm of another sun, whispering that the universe is stranger, deeper, and more alive than we've ever allowed ourselves to believe. Maybe impossibility isn't a failure of nature, but a mirror, showing us where our understanding ends. Do you believe this discovery changes everything, or is it simply another cosmic coincidence? Tell me below.